Hey everyone, thanks for joining us for today's conversation in which we will be focusing on cosmology, all sorts of questions relevant to how the universe began, the nature of time, the arrow of time, the origin of structure in the universe, whether our cutting edge description of cosmology is falsifiable, testable, issues perhaps of the multiverse as well. And I'm so pleased that the person I'm speaking with today is responsible for the dominant cosmological framework that really has been in place for something like 40 years. And that is Andreas Albrecht, who is at the University of California, Davis, where he is the distinguished research professor at the Center for Quantum Mathematics and Physics. He's renowned for, among other accomplishments, his contributions to the development of inflationary cosmology. And he joins us from his home in California. So it's good to see you, Andy. How are you?
I'm great. Great to see you, Brian. How are you doing?
Thanks so much for joining us. So as you just heard, we're going to, for the most part, be focusing upon cosmology and inflation. I wouldn't mind beginning, if it's okay with you, with just a little background on yourself. If I'm not mistaken, you were actually, you spent time in Ithaca as a youngster, where I had my first faculty job.
Yes, I grew up in Ithaca. I was born in Ithaca. I spent most of my childhood there, and I ended up going to Cornell. So I was regarded as a townie among my undergraduate friends.
Yeah, so you're both. You're both a university student and a townie. And your dad was on the faculty? Is
He
that
was on
correct?
the chemistry faculty at Cornell, and my mom also had a remarkable story. She went as far as the postdoc at Harvard doing biochemistry, stopped it all to raise a family, and when she was when we were older, she became a lecturer at Cornell and taught biochemistry.
And that was at a time I would imagine there weren't too many women who were teaching biochemistry in those
That's
days.
right. And one of the pieces I wish I had asked her when she was around was um, what it was like to after to drop for 20 years and then catch up on biochemistry in 1978 or whenever she was doing it, and that must have been just amazing. There
Yeah,
must have been so many things they only could wonder about when she was a postdoc, which were resolved.
right.
So
So in order, I get what you're saying, in order to teach that class, she had to learn what had happened in the years when she was raising you.
yeah, I remember her sitting there um, with textbooks on the kitchen table, reading up on
Really?
biochemistry, and I wish I had thought to ask her, what does it feel like? She was
Yeah.
clearly enjoying it, but
In our field, if you were to go back 20 years and then just try to catch up, I think it would be too daunting.
yeah,
There's just so much that has happened. So you have to have a certain kind of, adventurous spirit
I
to
think
be able to
I
come back in.
that's kind of why I mentioned it. Yeah, it's sort of the adventure
Yeah.
spirit
Yeah.
that I love.
Yeah. Yeah. No, it sounds like a real bold go getter to be able to do that. And so you went to Cornell. Did you go to graduate school at Penn? Is that
Yes, yes.
was
So
that the next step?
that was the next step. Yeah.
And what were you initially thinking of studying? Did you have a
So so
direction
so
that
I
you?
showed up at Penn with this lovely sort of innocent view that all of physics was wonderful, and I could do any. I had no attachment to any kind of physics, and and I actually had a difficult start in graduate school. I didn't get really fired up. I was sort of performing in a lackluster way, and I remember my academic advisor bringing me in saying, I'm surprised you're not doing better. And he said, "Do you have any idea what's going on?" And I wasn't sure. He said, "I think you're just bored," which I thought at the time was this ridiculously generous interpretation, and I was just thinking, God, this isn't going very well. But I think he was absolutely right, and I actually got really
Yeah.
excited by a group theory class that Tony Z taught. He was at Penn at the time, and it really fired me up, and that kind of shifted everything. I can tell you that when although I also had lots of ups and downs, so I did really terribly. They decided to have a sort of oral exam for entry into the theory group, and I did really terribly on it. And I think objectively that was true. I don't think there was any room for a difference of opinion on that. And I was feeling really at risk of being thrown out of at least that group. And so I kind of had to navigate that, and I really wanted to do particle theory. That was my so I developed, thanks to Tony Z and thanks to racings, really developed a passion for particle theory. I actually asked Tony Z if I could be a student, and he was leaving Penn, so that didn't work. Mm-hmm. I had a really great relationship with Willie Fischler, who was on the faculty at Penn then, but I don't know if you know his story, but he actually he as a Belgian, he had to go and do his national service. He had been postponing it year after year, and he so he disappeared from my life, and so there were these great rumors that a fantastic new person was joining the theory group, which was Paul Steinhardt, and don't forget, this was before the internet or anything, so rumors had a whole different flavor.
Your information source.
Yeah, right. And so I show up, and I made sure. So I was really feeling on edge about how things were going, and I made sure I was the first guy to show up at Paul's door when he arrived. And he said, "Well, I'm not doing particle theory anymore. I'm doing cosmology." And I had a really negative feeling about cosmology. It had. My only exposure to it had been for like a week in an astrophysics class. And I had the feeling that it was a subject that had these wonderful big questions and no way to answer them. and it didn't, whereas particle physics had accelerators and the standard model and all these, it was really happening like a real physics field. And so I was crestfallen. So I was there in Paul's office, and I was crestfallen to know he was doing cosmology.
And did he explain to you that he was thinking on the verge of?
So what happened for me was two things. One was I thought he just might know more than I did. So I was humble enough to right. Tune into that point of view. And also I was desperate because I had sort of been using up my chances in different ways, or the world had used them up for me. And so I told him, I swallowed my disappointment. I said, I'd love to do cosmology with you. And only later did I understand what a great, great that was. Yeah.
Yeah, that was a fortuitous answer to his change of direction. And so this is a time, obviously prior to inflation taking off as a way of thinking about it.
Not prior to Alan Guth's.
So this is post Alan's paper, but before your own paper then. So it's in that window.
Yes. And right? In fact,
okay.
I don't know how much storytelling you want, but I had
as much as you want to give. Sure.
So as a student, you could join the American Physical Society, and someone urged me to do that. And my first issue, or one of my first issues of Physics Today that arrived, had this rambling article about the boojum. He invented
Merman.
David Merman wrote a rambling article over many pages about how he got Physical Review to accept the word boojum for some theoretical construct, and I was so annoyed by that. So I had very, very strong views. I had views that I was so eager to have a successful career in physics, and that people who had it shouldn't waste their time writing articles about silly names. And so I actually canceled my membership to the APS. But in that little window, my first copy of PhysRev D arrived, and it was the copy with Alan Spaker in it.
Right.
So, so, so inflation was just sort of chasing me down.
So given that, can you just give us? I mean, obviously, cosmology was already a field in progress. You know, obviously, Big Bang cosmology dates way early part of the 20th century, but there were a handful of problems that people had put their finger on that the standard Big Bang approach seemed challenged to address. And that motivated Alan to write that paper that showed up in your fortuitous PhysRev D copy. I mean, I don't know that we want to go through all of them, but I think a big one, especially to motivate inflation, is trying to understand the horizon problem. You know,
But,
why one part of the sky is so similar to the other.
by the way,
Yeah, please go
I
ahead.
can also slip in that Alan refers to a talk at Cornell that influenced him to think about these problems.
Bob Dickey talk, right?
Yes, yes. And I was at Cornell at the time. I was sort of curious to go to that lecture, but something had happened to get in the way. But I was curious enough to ask someone who had a fellow undergraduate who had gone, what was it like? And he said, "Oh, some weird thing about large numbers or something." So it was someone who dismissed it, and but it's funny how those things
Yeah,
we're sort of swirling around, as you say. These things were swirling around. It was very influential for Alan
yeah,
to be
for
able to
sure.
lecture. And
Yeah, I guess Alan was working with Henry Ty
yeah,
around that time on various things, I think, to do with phase
right.
transitions in the early universe. And as I recall, yeah, I think it was the Bob Dickey talk that really made him realize there were some issues that one could try to address as a theorist.
And one of the things I find remarkable, and I imagine we're going to get there in this conversation, but I think so. Now, having thought a lot about all these issues and how one might try to address them, I'm very mindful of the fact that these kind of questions are very different from questions that are asked in other parts of physics, and it's I think it's fair to be doubtful whether they're good questions to wrestle with. I think that's an important part of the conversation we should be having is what questions should we be wrestling with, and which ones are promising, and all of that. And I went to track down these oral histories where they
Yeah.
interview people, and I found Dickey's reflection on that talk, and I imagined he could be sort of running a victory lap and saying, "Look, I planted the seeds, and look at all this great stuff that happened." But the tone that I got from that interview was he was still not sure what to make of those questions. Had a very humble and I think very appropriate sort of curiosity and puzzlement about is it what do these questions really mean?
Is that because these questions are, in some sense, fine-tuning questions
That's
that, like the
exactly
Big Bang could explain everything so long as you put appropriate initial
yes,
conditions in,
yes,
because you can make the initial conditions such
the
that they
right one.
generate
You can choose the right
2
ones.
points in the night sky having. Yep,
And if you
yep,
walk the halls of a physics department and look at all the other subjects that are being discussed, that's good enough. You have the equations, you choose the right initial conditions, and you're done. And the big deal is if you've got the equations right. That's what people are working on.
yeah,
And the initial conditions are there's this interesting in other areas of physics, the initial conditions they're how you set up your laboratory. Well, no, you don't have mystical questions about that. You set it up the way you wanted it to. You set it up in order to test, make a good test of your equations. No one scratches their head and asks why is a proton shooting down the beam at some high energy at CERN. We made it happen. We don't question that. We celebrate the success of the physicists and engineers who made it happen. Of course, the thing is, for the universe, it's not our project. It's the universe's project, and I think the thing is that so many things trace back to how the universe started, that there's so much riding on it. I mean, I like to but sort of one of the little narratives I like to give to illuminate this kind of question is, I could say, well, I just got back from a trip, and there was this guy sitting next to me on the plane, and of all the billions of people in the world, it was that guy. How could that be? And of course, there's got to be some guy,
Right.
So it captures that flavor of like, should I worry about it or not? What is an important coincidence to puzzle about, and what is not? And another example, I don't know, maybe I'm rushing this a bit, but I'll just say another illumination that I like to give is, suppose you come into my office and there's a pencil balanced on my desk on its point, just balanced there, and we, you're kind of curious about it, but we have something important to talk about, so you kind of ignore it and we have our conversation. And then you come back 2 weeks later, and it's still there, just perfectly balanced on its point. And you've had enough of it, and you say, "Hey, Andy, what's going on with this pencil? Has it been really balanced for 2 weeks?" So what if I said, "Oh yeah, it was like that when I moved into my office. It's just kind of odd, but it was just like that when I moved into my office, so I don't have to explain it. It's just the way my office is." You wouldn't accept that.
Right.
You'd say, on the other hand, if it was just kind of tossed on the floor in some random way, and if you asked me, "Andy, I know we have some science to talk about, but I'm just so distracted. Why is your pen this way on the floor and not that way?" That would just be dumb. So it sort of illuminates the kind of things we wrestle with the cosmos.
Now, when you put that into scientific terms, and those everyday examples are really illuminating, but of course, they are symbolic. They're representative of a real concrete scientific question, which has to do with entropy.
Yeah, so we have very technical ways of studying this. And yes, and my favorite, so there are tuning problems that are expressed in a lot of different ways, and I think you mentioned the horizon problem. There's sort of different ways of doing that, but my favorite way to really, I think that really gets to the crux of it, is to talk about the entropy of the universe. And not only does it, I think, get to the crux of the nature of the tuning that we talk about, but also to the crux of the way it seems very complicated to address, the nuances of whether or not it's a legitimate question.
Totally. Maybe even just start again. The people who are watching, some are deeply familiar with entropy and the second law, some are less so. Maybe just give us a thumbnail sketch and
Sure,
then talk about how it's relevant to the universe.
sure. Well, maybe something to talk about is just putting milk in your coffee. So if I have a cup of black coffee and I put a little milk into it, I can stir it up, and it changes color, and the milk gets mixed all the way around. That's something that we can't possibly reverse. It's a very straightforward physical process that we cannot run in reverse. If you were to capture, I remember when I was a kid in school, they'd show these ridiculous educational movies. The big fun we had and it's interesting because maybe that's a precursor to my career. The fun we could have is if we could persuade the teacher. The movies would come on a reel of film, and part of the job was to rewind it after we watch it. And if we could persuade the teacher to rewind it by running it back through the projector, we could watch the whole thing in reverse, which was hilarious. And that's the thing.
Hey, Andy, we have one of those. Can we show you one of those just for the fun of it?
Yeah.
Do we have that? Do we have that wine glass?
Oh no, with the wine. And
That's what your
everything.
teacher showed, and then,
Oh,
yes, and then oh yes, there it is. All those little particles are coming back together.
yeah.
Yeah, you never get tired of seeing
Never
something
got
like
tired
that.
of it.
Yeah.
So there you go. So the so this is so much part of our everyday life that we know it goes one way and not the other. In fact, it's so much part of our everyday life that it's very hard if as a physicist we're trying to develop a theory where we're not assuming it in the outset. It can be very hard to do because we let it slip in. It's so much part of our intuition. And I love Lenny Susskind has a term he uses for that, which is temporal provincialism, something that apparently comes from literary criticism. But he says we're provincial in the sense that we have an arrow of time, and we're so used to it, we have trouble setting aside the intuition that comes from that. So yes, so we have a very clear experience in our world where time goes one way and not another, and there's a technical approach to understanding that physicists use called entropy, and in roughly speaking, it's a measure of the onset of disorder, and you saw the disorder in that wine glass for sure. There's also disorder in the milk, mixing the milk and the coffee, and sort of any of these other examples that you might think of. And I think I actually I have a TEDx talk where I play with that. So that's another place people can look for some fun with the destruction that creates disorder and so on. But the technical analysis of such things uses the term entropy, and we say this clear direction of time going one way and not the other we call the arrow of time. And in the world of physics, we talk about the second law of thermodynamics, which states that the entropy will always increase. So the second law of thermodynamics captures this intuitive thing we have that certain, lots of things go one way and not the other. So so for the universe, things get pretty interesting because entropy and gravity have their own special relationship, and there's a whole that's a very interesting and even not completely resolved set of questions associated with that. But you need to delve into that to think about the entropy of the universe. And when you do that, you see there's certain ways where the entropy is very, very low at the beginning of the universe. There's other senses in which it's high. So it's really sort of in the middle in the early universe. But crucially, there's a sense in which so in some sense the gold standard for high entropy is a black hole, and that comes from if you have a bunch of matter and you want to make the highest entropy state you can out of that matter, you should make it into a black hole. And so basically the sense in which the universe is low entropy is that it's all this matter. There's lots of matter in the universe. We don't know truly how big the universe is. It might even be infinite. But there's all this matter, and in the early universe, it's spread smoothly around, and definitely not a black hole. And that's the sense in which the entropy is low, and the formation of structure in the universe, the collapse of that matter into objects like galaxies, planets, stars, and so on, and black holes for that matter, is how the entropy increases in the cosmos. And in fact, today, the most of the entropy in the universe is in the black holes at the centers of galaxies. So it's
Right.
come a long way from this low entropy start. And you could say, well, good thing. I mean, if you think about the arrow of time, it's an important part of our lives. And I like to, I don't know how technical we should get about that in this conversation, but
You can feel free to. Yeah.
but
Yeah.
for example, our metabolism depends on the arrow of time. If you think our metabolism isn't that different from an internal combustion engine in sort of abstract terms, and if you think about the internal combustion engine, you ignite the fuel and it pushes a piston, and if that thing were in equilibrium, there'd be just as much burning fuel outside as inside the piston, and the piston wouldn't know which way to turn. It would just fluctuate with thermal fluctuations, but you couldn't build an engine without the arrow of time. And our metabolism is another kind of engine. And you can say the same thing about if you make an X on a paper. Let's talk about making a record and storing information, and let's just abstract it to writing an X on a piece of paper. If there was no arrow of time, the ink could just pop right back into the pen. there's the stability of that mark on a piece of paper really comes from the arrow of time, comes from the fact you've increased the entropy of you've sort of energy from making the mark is dissipated into the many degrees of freedom of the paper and the ink, and it won't easily, it's ridiculously improbable that it will randomly come and pop back out and remove the record that you've made. So, and I would say, there's all kinds of different ideas people have about where our mind lives and what kind of thing our consciousness is. I tend to take a very physical point of view that our consciousness
Me too.
is physics that happens in our minds and bodies. And so I would say that the psychological direction of time, the idea that I sense I can remember the past and not the future, is exactly it's exactly the thermodynamic arrow of time, the physics arrow of time, which I just sketched with the pen marking the paper. So I don't know exactly how my memory works, but I'm guessing from a physics point of view, from an entropy point of view, it's the same notion as a pen marking the paper, and something has to dissipate to stabilize the record. So I really feel that we depend entirely on the arrow of time to exist as we do. We have the concept of our existence outside of an arrow of time is meaningless. We're creatures of the arrow of time, and so lucky us that we live in a universe with an arrow of time. Now, as it turns out, the same concept is also how we can express the tuning. So the tuning, as I've sketched with the pencil balanced on its point, is about being in a special place that seems somehow unlikely. Low entropy. So entropy can be thought of as a measure of how many possible configurations a system can have, and still have the properties that you've noticed about it. And so there's many more configurations of milk and coffee where it's all mixed in thoroughly than there are if the milk's just in one plop in the middle. And there's you can go on and on. There's many more configurations of the energy in the mark you made on the paper, where it's dissipated in all those internal molecular degrees of freedom of the ink and the paper. So you can say that the increase of entropy moves toward directions where there's more available states, more possible configurations for the matter. And so to have a low entropy start, we need low number of configurations. And that is what tuning, that's the essence. When you could take, these tuning conversations take different forms, and they might be not familiar translated in this form, but I could sit down with you or anyone who's worked on this stuff and translate it. So it really is entropy. And any one of these things are, at the end of the day, about entropy, and they're about the small number of configurations available to the universe as we know it at the beginning compared to what's available now.
So I gather one way of framing the puzzle or the issue is, like you said, if that pencil's standing up on your desk, low entropy configuration, I walk in it's curious to me and I want to explain it. Low entropy in the beginning of the universe, is that really analogous to that? Does it really need an explanation? And I think many people think the answer is yes. But like you said early on, it may be worth questioning that, because it could simply be like that person sitting next to you on the airplane. It just is the way it was. It was the way it was, period, end of story. There may not be a deeper explanation, but if we can find one, we should try to develop it.
And I think an important difference that's illuminated by the pencil example is that the contrast between the pencil balanced on its point and the pencil just tossed on the floor is that the pencil balanced on its point is unstable. And so our curiosity is drawn, like, how can you balance it so carefully? Anyone knows how to toss a pencil on the floor. No one knows how to put a pencil up so it stays for 2 weeks.
Right.
And I think, on the other hand, if it were just like the pencil tossed on the floor, it wouldn't have an arrow of time. So the arrow of time, the fact that there's a forward direction, a thing that happens, a thing that has to happen, the pencil has to fall over, the entropy of the universe has to increase. That's what we live by, the arrow of time. So it's an interesting situation. I think what I like about the pencil on its point example is that you couldn't, if that really were to happen, you couldn't stop being curious about it. And that's what we're like as cosmologists. It's really hard. You can say, I don't think you should ask those questions, but it's really hard not to really stop.
Do you think that inflation addresses the entropy low? Because in many ways, you can argue that the inflationary scenario needs yet lower entropy configuration to tack on to the more standard Big Bang theory.
So this is why I like the entropy argument so much, is it makes it really clear what concerns I have about inflation. And I think it's really, and I think, people can be applying the concepts of entropy to inflation can lead you into kind of uncharted territory and so on. But there's a simple piece to the story, which is that regardless of what you think you should say about entropy during inflation, everyone agrees that inflation ends with a massive increase of entropy, at which point at the end of which the universe looks like it did in the standard Big Bang before we thought about inflation. And so whatever you can say, the entropy is definitely lower. If the entropy shoots up and then becomes exactly like the entropy of the Big Bang, then the entropy was lower to begin with. And so in that sense, I would say the inflation looks more problematic from that point of view. It's not how we, it's sort of, there's not many people. I'm glad you appreciate that point.
There are some people who have tried to argue that maybe the way to frame it is not the amount of entropy, but the amount of entropy relative to the maximum possible entropy in a given epoch. And some have tried to argue that the gap in the inflationary scenario between the maximal entropy, because the universe is so small at the beginning and then it undergoes this rapid change in size, that the entropy gap is something that is not as large as it would be in the Big Bang. Is that a way of thinking about things that you think helps to
So
alleviate the problem or the puzzle?
I don't think we understand. I'm glad people are trying it. I don't think we understand it well enough to know how well that's helping. So it's a, yeah. I think I think so I don't find myself really captivated by that way of thinking, but I don't I definitely don't ignore it either. I think we need to be looking for
Right.
fresh ways of thinking about it, and I think we're so. I personally feel quite ill-equipped. I don't think anyone is better equipped. I think we're ill-equipped to really navigate that kind of stuff with confidence, and 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 so I think it's a mistake to be dogmatic about it. I think people should be trying different things,
Yeah.
and I like that. I guess I'm pretty intrigued by that idea, but I'm not quite sure what to make of it.
The other idea, just to throw things at you, that because I've you and I have discussed this over the years, although not in a long time. We haven't had a conversation in many years about this. But there are also people who have tried to argue that maybe our intuition that low entropy is sort of rare or unlikely, maybe that needs to be challenged. In the real world, certainly low entropy things, fewer number of states, almost by definition, it seems relatively rare. But we are assuming a measure on the space of possible configurations. And to say that entropy is the right measure on that space may be biasing our intuition. And it could be that in the early universe, with 100% probability, we know it began some way. And maybe there's a different measure where entropy would not be the delimiting quantity that would be used to determine likely or unlikely. Do you think that
I'm
helps?
also curious about that. I think um, that would. I mean, I do think entropy, as we've been discussing it, is a good way of articulating the tuning problems. But in a sense, what you're saying, you're kind of saying if we understood it correctly, if this were the right way to think about it, you'd be saying what tuning problems, basically,
Right. Exactly.
and maybe that kind of feeds this. I mean, we've had this give and take about how legitimate these problems are, and that would be sort of one way. And I would say, when you get into the nitty gritty of how you try to wrestle with these things, I always like to say that the straw man, the sort of theory to beat, is just the good old fashioned Big Bang model that you and I learned in a class long ago, and just choose the right initial conditions. We were talking about choosing initial conditions. Most physicists are good at it. They don't apologize for it. They choose the right initial conditions. And from that point of view, we're done. We've done cosmology. We have good equations of motion. We know what initial conditions they need. And so, how is your theory better than that? Is sort of the question I pose myself. Yeah. It's a question I ask myself. How is what I'm doing going to be better than that?
And what's your best answer to that question for instance, obviously inflation is something that has been important to your career, to your life. What is your most optimistic answer
Well,
to that
yes.
like inflation?
So this is the perfect question, because I've been itching to circle back a little bit and say some of the things that I think are really awesome about inflation. And it's
Yeah.
and I would say inflation kind of stuck its neck out in terms of addressing the sort of interest started with the tuning problems, at least on certain. We both know that there's actually a number of different paths where people arrived at the idea of inflation, and some of them are remarkably different. But the path that a lot of people know, and the way it's usually taught now, is through these tuning problems. But there's another thing that inflation does, which is it gives us a very concrete way of thinking about the state of the universe that describes the galaxies and clusters of galaxies and all of that. It gives us so basically the idea is that during inflation, things that are on very, very small scales in the universe get expanded to all observable scales. And so there's a remarkable so you could so in this straw man I gave you, the origin of the galaxies, clusters of galaxies, and so on, is something you put in by hand. You just say, what initial conditions do I need for this kind of stuff to form? And we know what we need. We know how to put that in. But inflation says, here's where those conditions, how they arrived. And it says they arrived by taking the microscopic properties of matter and spreading it out across the entire observable universe. And so I like to say there's producers and consumers of inflation. And mostly there are consumers at this point. And consumers of inflation like to take data and like to put theoretical curves through it. And they're happy. Like they've got what they want. And you can use inflation to put a theoretical curve through all kinds of data. It works very well. We can talk a little bit about the flexibility, and people argue about what kind of flexibility there is, but there's no question that you can take some data, you can find a curve that fits it well, and you could say, for this curve to fit well, inflation had to have these properties. And that's a very, that's bread and butter physics. This is a very satisfying thing to do. I have a little bit of regret that what happens with these consumers is, for the most part, these tuning puzzles, the way they've seen it is they've had a class, and one day they talk about the puzzles, the tuning puzzles, and the next day they say inflation solves them, and they never think about it again. and they don't want to think that their theory that's serving them so well as consumers has these difficult, exciting questions unanswered. So there's sort of a interesting cultural phenomenon that happens where inflation is sort of entrenched in the minds of people who find it very useful and don't like thinking about difficult questions. But different colleagues, as you know, respond differently to that situation. I have a pretty lighthearted feeling about it. I'm glad they're doing all this work. We're really lucky to have all this data, and it's I imagine if you spend your whole time worrying about entropy, it might not be so easy to do all the hard work that goes into collecting that data. So it's great. It's great that we have these different roles. But I wouldn't mind seeing the culture a little bit more curiosity about these difficult and unanswered questions. But I want to circle back a little bit. So one of the important details of how how this whole picture works is that when I tell you the microscopic properties of matter get stretched across the universe, you know exactly what I'm talking about. And every physicist agrees that if we look down deep at small enough scales, we expect all the quantum fields that describe all the matter to be in what we call the vacuum state or the ground state. And there's no doubt about that, because these quantum fields do a fantastic job of describing all the matter and forces around us. And the only way they do that fantastic job is by embracing this feature that you need to understand that on the most microscopic scales, all these quantum fields sit in a particular quantum state called the vacuum state. And so when you start inflating and you ask what what shows up on all these observable scales, it's the vacuum state that gets stretched. Not some other state, not some random state. It's the vacuum state of the quantum field theory that gets stretched to all these cosmic scales. And so in a world where you might be scratching your head, why is the universe in one state rather than another, and do you have to choose? Can you just decide what it is, and do you have to worry? There's one state in the world of physics that no one questions, and that's the quantum vacuum, the quantum field theory vacuum. And so inflation does this clever trick of importing, like the one, if you're going to move among physicists and let them choose one state that they talk about and don't worry about why is it this rather than that, it's the quantum vacuum, the quantum field theory vacuum. And so inflation harnesses that sort of cultural fact. So I would say you could ask, why is the quantum field theory in the vacuum state rather than something else? But we just know better because it doesn't work. It's just a practical thing. It's the wrong theory if you don't choose this vacuum state. And so it's sort of, I would say, it kind of sneaks in this cultural fact that we know something simple about the universe, and it imports that to the entire cosmic scale, and it works. It's not just that it's a cute idea, but it actually works, and it serves these purposes.
And just to show that, Andy, do you mind if we show a little graphic?
Great.
The prototypical example is you take the microwave background radiation, but I'll let you describe the graph that's coming up, which takes that quantum ground state of a quantum field, stretches it out, and says what it does to the temperature variations. And that's the theory. Then you do the observation. And this is illustrating your point of it really works. Look at how the observations and the math curve are right on top of each other.
Yeah. Well, there's so many dimensions to this. For one, a remarkable feature of, we call it the quantum vacuum. It's very different from vacuum. We imagine sort of colloquially a vacuum is just nothing, but in quantum field theory, a vacuum is something. It's a particular state of matter, and it has fluctuations in it that have a particular characteristic. So when you stretch it across the entire observable universe, you have there seeds, variations in matter density that can collapse and form galaxies and so on. And the map that we saw just a moment ago is very early evidence that. So this is an image of the universe several billion years ago. The light that was emitted several billion years ago when not much of the structure had formed, and it really is an image that these. If you look at the variability from the hot and cold, so this is really a measure of temperature, and the different temperatures I've measured are indicated by different colors, but the variability across the different colors is 1 part in 100,000 or so. And so you're looking at very, very subtle variations in the temperature of the universe, and you can analyze that. You can quantify that by asking, well, for a given size fluctuation. So as you go, choose a little size region and place it on different patches of the sky. This is, by the way, if probably most people have seen an atlas, a map of the world where it's spread, the sphere of the Earth is spread out onto a flat page. This is now, if you think of the sky, we look up at the sky, but you could look up in all directions, and the sky is really like a sphere surrounding us in all directions. And this is the sky spread out onto a flat page, just like you would a projection in an atlas. And so we're looking at temperatures all around us, different points in the sky. We can choose a given size region and ask how much is the temperature varying as we move that region to different parts of the sky. And the curve that you showed is called a power spectrum. and roughly speaking, the x-axis is size of the region, and the height, the y-axis is how much variability there is. So it's really taking this beautiful map and making something very quantitative of it. So the patchiness that looks kind of cool and so on. The power spectrum is a big step to turning that into real quantitative science, and asking what characteristics does this patchiness have. When we look at that
Yep.
curve, we see there's some pretty interesting features that on certain patches there's much more variability than others, and the degree of variability kind of wiggles up and down as you go to different sizes. So it's a very striking characteristic, and maybe this is a good moment. So there's a lot of conversations that happen around the fact that this plot shows the curve that fits, but there's other inflation models that could give different curves that don't fit as well or don't fit at all, and so people can have conversations about whether, what is inflation predicting versus what is just a fit and all of that.
And can we hold? Can, can we drill down on that? Because I think it's such an important
Yeah,
point that often gets glossed over in these conversations. Because inflation's really, I think you agree, it's a paradigm. It's not a specific theory, and it is partly characterized by the energy curve, the so-called potential for the inflaton field in the simplest one field models, to use the technical language. So if we can bring up just some of the potentials that one could write down. We have some graphs as well. So you mean just, you can take it from here, Andy, but the different models are characterized by the different shapes.
physicists have been rewarded for for creative work in building theories of quantum fields, and so we're very good at that. And I say rewarded because every time we got confused, we added another quantum field, and if we added the right one, things started making sense. So the history of particle physics is to reward people who are able to creatively imagine new theories of quantum fields, and sure enough, there's been success stories where people got confused and then invented another field, and it turned out to be real, and goes on. So we're very, very good at inventing quantum fields. One of the ingredients that goes in is something called the potential, and so to draw a curve like the one we see as part of the theory is a very straightforward, very normal, everyday thing, and we can draw just about any curve you can imagine, and imagine that it's part of the theory. Now, to be a little bit more rigorous, some of the curves are going to have a sounder footing than others, and so on. So you can dig down into that. But the world of inflationary cosmology tends to play pretty fast and loose with the freedom to choose these different curves as part of your fundamental theory, um, and that will translate into different looking curves for the power spectrum that we were just looking at.
But I do want to ask, because sometimes people draw the following analogy. They say the standard model of particle physics that we view as the gold standard of a theory that has been rigorously tested and confirmed through experiments, as you and I and everybody else, of course, who works in this material knows, the standard model of particle physics has all sorts of constants within the theory that can be adjusted, that are analogous to changing the shape of a potential energy curve. And people say, well, that's fine. What we've done is we've used the data to nail down those parameters, and then we make further predictions, and we're done. We don't have to worry that there's a flexibility in the physics that underlies the standard model of particle physics, which is quantum field theory. Should we take the same attitude here? We just look at the CMB, figure out what potential energy curve is able to match it, and then sort of say, hey, we're done. We're done, right? We've been able to explain the hot and cold spots, and that's enough.
So I think I'm fine with that, but I can do better because, as you know, years ago I worked on a competing theory, um, roughly speaking, cosmic strings or cosmic defects. And one of the um, projects I'm especially proud of is that we were able to show that these special wiggles that we were just noticing in the power spectrum can't appear with the competing theory. So I think even though there's a lot of flexibility in the inflation picture, there's not arbitrary flexibility. You actually, those wiggles are a really important physics process. The fact that there are those wiggles there reflect a really concrete physics process that you're stuck with when you have an inflation theory, and other theories wouldn't have that process, and so it's a little bit better than what you say. I think what you describe is good enough, that you have theories with parameters and you can adjust them, but you can't adjust away those wiggles entirely. And so I think it's a little bit more than that. It's a pretty exciting thing. And so I think so we've just been discussing some of the nice, that's pretty special. Like if we ask why, why do galaxies form in these patterns and not those patterns? Why are there these particular patterns in the microwave background radiation? We have an answer to that. We say it's the quantum vacuum state stretched onto the entire universe by inflation. And by the way, if you think about some of these competing ideas like cyclic universes and so on, they all share that feature, that they are finding one way or another to stretch the quantum vacuum across the entire observable universe. And so even though they're members of our community that love to debate which is better, to me the most deeply interesting part is the success of stretching the quantum vacuum out to cosmic scales and how well that works. So to me that's really exciting, and we don't, maybe inflation did it, maybe something else did it, but that's a tremendous step forward, I think, to actually have something to say rather than just putting it in my hand. So we already know that we can do better than all the other physicists as we walk up and down the halls and they just say, well, choose the right initial conditions and get on with it. We can do better than that. We can have a story that these initial conditions came from the quantum field theory vacuum. And that's pretty special. And I think, part of when I say I'm not sure if worrying about all this entropy stuff is really the right thing, part of what encourages me to at least spend some of my time thinking about it is that there's other aspects of inflation that work so well. I mean, this quantum vacuum thing, or inflation or other models, it's such a sign of success that I think we owe it to ourselves to keep pushing. We've gotten somewhere interesting. We should keep trying and see where it leads us. I don't think this is the time to shut down and lose interest.
Now you mentioned, the cyclic cosmology, and famously, Paul Steinhardt, who you brought up early in our conversation, the person whose office you were there first to try to work on particle physics, and then he turned you toward cosmology. And your paper with Paul, of course, was one of the two papers that introduced the more successful version of inflationary cosmology compared to the original paper of Alan Guth. Paul himself, as of course you know well, has changed his perspective, I think, on inflation pretty dramatically. He doesn't just question it, he's fairly negative on inflation these days and is really promoting this other idea that he and other collaborators have developed, the cyclic cosmology. Where do you stand on that?
So I actually, my view is that when these tuning, so I'm still learning. I think Paul's thoughts have evolved, and I'm not sure I know the latest, but a lot of his critique of inflation surrounds tuning problems, and I feel that they're absolutely legitimate problems. I I feel that, or I feel that they're really there. Whether they're legitimate questions is another question. But I think, and I feel some of the energy he puts into this comes from his frustration that people aren't willing to just talk openly about it, but they're sort of a stubborn defensiveness about these things that are and I agree that it's really annoying. I think I feel I tend to feel a little bit more that the people who are being so stubborn are sort of making fools of themselves, because these questions aren't going to go away. and we're scientists, not religious dogmatists, and so these the questions aren't going to go away, and so trying to be so protective isn't, I don't think, is sort of foolish. But I do think that the ideas that Paul has been promoting have the same problems, and you could argue even have them worse. And so I think he's been navigating a particular path where he um, sort of recognizes a certain feature as a partial improvement, whereas I look for the whole thing. like if basically if you have a big arrow of time, you've got tuning problems, and whether you've finessed things a little bit here and there along the way, I'm not so. It's just not as captivating to me, because I sort of feel like these other problems, if they have a solution, are could bring something really big into the theory, really something exciting, new, and special. And I want to know that thing. I want to be there to help discover what that big different thing is. And I don't want to get busy debating whether sort of these little sort of epicycles here and there are going to make a difference.
Right. But let me ask you, though, as well. So, we live in a world where, conspiracy theories grab people's attention. People will click on something that say, physicists have been hiding something vital from us, all sorts of nonsense of that sort. On the other hand, there really is in this field more than in others, I think, and it's pretty much what you've been saying as well, a certain kind of reluctance to really take a sledgehammer toward the foundations of inflation and just see how strong it is. And when you do that, you do recognize that there still are issues having to do with fine-tuning issues and initial conditions and so forth. Why do you think there has been a certain reluctance to really fully examine these issues, at least on the part of some people who've been pushing these ideas forward?
Well, I like the way you've introduced this topic, because I think I tend to actually be try to be understand. I think we all need some things we just have to believe without questioning, and I think as scientists we like to imagine we're not like that, but we are. We need reference points. I mean, if I if I got all confused about which side I wanted to get out of bed this morning, I wouldn't be here, right? I'd still be in bed trying to figure out how am I gonna get out of bed, and so I just did it. I didn't question it, and there's a million things like that where we actually do we do just take ideas for granted. So I think it's more of a question of which ones, and we do get protective. Like if you if my wife came in the morning and said, "Andy, are you really sure you want to get out of bed this way? There's this other side over here. You could crawl over. You could go off the end. Come on, think about it. Don't be so dogmatic." I would have said, "Stop it. Don't. I'm not going to explain. I'm not going to explain to you why I'm going to make this choice. I'm just going to do it. It's my dogma." And so I think we all are dependent on assumptions to journey through each day, and I think the question of which assumptions we make and who's trying to impose their assumptions on us and all of that. I mean, I actually try to, you know, you mentioned the political context. I know we can't really, I probably neither of us really wants to go too far into that in this moment, but I think the question of sort of one group trying to impose their beliefs on another is part of the human drama, and not not something we can escape. I think you can escape it by having one group think they've won, but it's not a that's not entirely stable, and so as we know, so I think, and I, you know, I think in the case of, so then there's sort of a case of what's at stake. If I can't figure out how to get out of bed in the morning, I miss out on all kinds of great things that could happen during the day, including chatting with you today. If I think what gets tricky in science, actually, I'll wade right into this one. You know, what some of the worst, most unpleasant conversations I've had in science have to do when you're sitting around at dinner after a conference and people are trying to figure out who should get the next Nobel Prize, because it's always a conversation where you're trying to make a set of results or ideas more certain than they are, and the people are trying to achieve a definiteness that is never really quite there, and whether it's a definiteness about exactly what role these ideas play or exactly who had the most important role in developing those ideas, it's something that I mean, I actually think the Nobel Prize is great because it sort of gives people a go to reference point for progress in science and people to refer to and all that. So I don't have a problem with that. But the conversations where people try to, you know, it's sort of, well, this is another topic. I don't know if we get to really talk too much about it here, but you know, it collapses the wave function. If you want to know what's a great recent progress in science, if you want to know who did it, there's an answer. But science is usually at least a little bit more messy than that. And even you know, you've mentioned two papers bringing influence to about inflation, but there's actually some more. and and
Sure.
and so we so I think the a lot of the protectiveness of inflation is also jockeying for recognition and you know, the need for it to be complete somehow to get the recognition. Whereas I think actually it's a shame, because I think the influence that it's had, and as I've said, this whole idea that you have something interesting to say about the entire structure in the universe is exhilarating and not something you could have anticipated. And in fact, to some extent, the fact that I showed up in Paul's office the first time with a lot of skepticism about the field of cosmology was exactly that intuition that how could you possibly answer that? And I think there's a case to be made that you can't, except we can. and that's magic. And to have done it, to have done it in a way that raises other challenging questions, so what? That now we get to work on those other challenging questions. It's a wonderful thing.
You know, I think it's very illuminating. And I do think it's important to draw a distinction between these natural human tendencies to want certainty, or natural human tendencies for work to be settled, because there are these prizes that recognize work that has achieved that level of being established, as opposed to what I sometimes see out there, which is willful misleading in order for some nefarious purpose. You know, it's not that. And I think that distinction
Oh,
is
you see
certainly
people
important
inferring.
to draw.
So you're sort of saying people are, yeah, and I think I I sort of have a social theoretic. I wonder if there's something about our
Go for it.
species where distrusting the leader is a so so in some sense people rise to the top by being really good at being leaders and sort of maneuvering into that position. And and if you're just not part of that leadership, you can't possibly figure out exactly if someone's right or wrong about everything. So there may be something very fundamental in our species that's distrusting the leader for distrust's sake. Some of our colleagues are sort of scrambling to protect an image of perfection for this theory, and maybe they're just expressing their human nature by wanting that, creating that defensiveness. And I would say I'm expressing my human nature by just celebrating that I get to be so curious about so many amazing things. And maybe it's just my temperament, That's how I like to. That's why. That's why I went into science to have adventures like this.
Yeah. It's interesting, Andy, that you say that, because I resonate with your description extremely well. And I have found the following, and I wonder if you have found it as well. When I have one-on-one conversations with almost anybody who has been or currently is, a leader in cosmological thought, there's almost no contention on these being important issues that really need to be examined more fully before we can really say that we have or don't have, a fully viable theory of cosmology. Sometimes in public settings, because I have these kinds of conversations, and like
Yeah,
we're having right now, that ultimately will be posted and be available to the public, it's a little bit harder to have that kind of a frank conversation. I think that fits into the human nature
yeah,
side of
I
things as
totally
well.
agree with that.
One to one as human beings, we can let our guard down. Yeah, yeah,
And I
yeah,
think I would even push that further. I would say there's certain characters, and it's probably just as well not to name names, but some of these characters we're talking about, I have absolutely amazing conversations with one on one. It's absolutely, we explore these things in wonderful, depth and with a lot of great curiosity. And I also, yeah, I think, yeah, that's absolutely right. And I think it's fair. So to me, what's missing that I wish I could sort of convey better to the community is that inflation is amazing. It's amazing with all its incompleteness, and
yeah.
that I think we should be able to celebrate that without pretending other things aren't unresolved.
And so, can we turn to one final topic? Because I know that you'll have to go in the not too distant future here. But I wanted to, I'd be remiss if we didn't discuss the multiverse as one of the other features that naturally emerges from many inflationary models, and has, polarized over the years physicists regarding whether they're willing to talk about the multiverse, whether the multiverse is metaphysics, whether it's physics. My own view is that it's an interesting idea that we should keep in our toolkit. If inflation truly is right and the simplest of models turn out to be correct, we may need to take the multiverse seriously as a natural consequence. Maybe it's testable. There are indirect ways that in the best of all worlds it might be testable, but it's very much speculative ideas that we shouldn't just rush toward quickly because it's a radical change in our picture of reality. I mean, how do you come down on the
Well,
multiverse?
I think a good place to start from my point of view is to say, I think physicists as a whole have a pretty conservative streak. We don't like to we don't like to embrace radical ideas unless nature is somehow forcing us to do it. We don't want to, you know,
Yeah.
if I said, Brian, I want you to hear my theory that the universe is really a rubber duck, you probably aren't going to have time for that. Or you're going to pin me down pretty quick. What on earth are you talking about? But I think with a lot of cosmology, we don't know how to make that conservatism. We don't know how to realize that conservatism. So you mentioned the multiverse, and what I'm imagining, the piece I'm imagining you're referring to is that if you take inflation at face value and you take a simple idea about inflation, you wind up sort of extrapolating in a really simple way and learning that our little bit of the entire universe we see is some ridiculously small part of a much bigger thing, and that seems very difficult to avoid. And I've done some work asking, so what, and that seems radical. Like who needs a theory of a universe that has so much more than what we see? It just seems, and especially there's at least perceived problems that it's actually sort of prevents the theory from having predictive power, and we can get to that. But I've tried to ask the question, what would an alternative be? How could you prevent inflation from generating the multiverse in that way? And you have to do something else really radical. So I'm actually pretty excited about that path, and I'm not. I think that might be, this whole tension might be pointing us in this other path where there's basically a breakdown. I would say, in fact, I think it might be even connected to these entropy things. I think I don't know if we get to use the term phase space or Hilbert space in this conversation, but it's sort of a
Feel free.
a way to describe, you have a physics theory, and the theory sort of should be able to describe all possible configurations of that theory, and you talk in quantum physics, we talk about the Hilbert space that kind of characterizes all those possible configurations. And maybe not surprisingly, that's connected to entropy, because you're measuring the possible configurations out of all possible. You sort of, it's the context by which you count possible configurations of the system. I'm pretty convinced that the entropy puzzles, the tuning problems, will not be solved with conventional ideas about what the Hilbert space is from quantum field theory or so on. I'm pretty convinced that there has to be something really different to ever solve them, if there is a solution. And so that could, and certainly these ideas that inflation leads to the multiverse sit very much on a foundation of conventional ideas about the Hilbert space for quantum field theory, or the whatever I'm supposed to call that space. Mathematically, I think they don't want to call it a Hilbert space, but something else. But it's so I think that these different topics we've talked about might come together to be pointing to a particular path toward a resolution. I'm certainly fascinated by topics in holography, and so I'm very curious about whether our pursuit of a good understanding of quantum gravity could be revealing alternate ideas about what the space of states is really like, and how that stretches back.
Can you go a little further in that? Are you reducing the Hilbert space in some
Yes,
dramatic
yes.
way?
So I am very fascinated by the idea that the Hilbert space is really finite, and so this comes, for example, if we just think about the dark energy. We've not talked about that, but there's an idea that there's a very popular idea right now that our universe might have something called a positive cosmological constant. if that's the case, supported by data and so on, if that's the case, then the future of our universe is, at least in simple terms, probably going to be something called a de Sitter space. A de Sitter space has a horizon just like a black hole, and with that is an associated entropy, just like with a black hole, and it's a finite entropy. And so there's a community that has proposed that maybe that fact means, so if the entropy, the maximum entropy of the universe is finite, then you would never need more than a finite Hilbert space to describe it. And maybe that's a hint that we're going to deviate, that the deepest understanding of physics is going to deviate from all these quantum fields. I mean, even a single harmonic oscillator or pendulum has an infinite Hilbert space. So saying the universe has a finite Hilbert space, albeit incredibly exponential of exponential large, but finite, would really mean a radical shift in the most foundational understanding of how the physics goes. And I've worked out some ideas about how such a truncation could also truncate the period of inflation, lead to a breakdown of the way inflation generates a multiverse, and also actually incorporated these into ideas that could help us understand the entropy, help us understand the tuning. And so I'm very fascinated by all these different moving parts. I don't know, you asked me to illuminate something. I'm not sure if I...
No, that's a good explanation, of how the coming together of observations. I mean, everyone was surprised in 1998 by this result that the expansion is accelerating, and everybody was deeply surprised that, it basically means that there has to be something like a cosmological constant that's energy suffusing space that Einstein introduced in 1917 and then threw away. And if that observation then reflects back on the allowed space of states in the quantum theory describing a universe that, as you say, will have a horizon. There are objects out there that will be moving away faster than the speed of light if they're sufficiently far away, if the expansion is accelerating, and we therefore in some sense won't see them. There'll be a horizon around us, and that would radically change the quantum field theoretic description of the universe in that setup. If that then impacts this issue of the multiverse in sort of the manner that you and others as well have played with, that's a deep possibility, again worthy of exploration, and it's by looking at a potential flaw, if you will, in inflation, that it gives rise to realms beyond the ones that we can see. If it could then give insight into what the right theory is, I mean, that's the dream of physics.
Exactly.
Right?
So it seems like our world as cosmologists is populated with these really exciting ingredients. I think you did a great job of just describing how, the cosmic acceleration, which surprised pretty much everyone on the face of it, has now stimulated all these different ideas, and ones that can circle back to connect to these other questions we've been talking about. So, God, what an exciting time! I like to tell people that, if I were to choose a time and a topic in the entire history of physics to be part of, I wouldn't change anything.
So look into the future, though, Andy, as we wind down to look into the future. I mean, is there one or a small number of questions that, if one, namely you, or if the community could find answers to, say, in the next, who knows how much longer either of us have on this mortal coil, but, in the next 20 years, what do you think we might learn? Or if you had your druthers, what would we learn?
So one of the things I'm really curious is whether our pursuit of quantum gravity will yield really alternative ideas to the Hilbert space. To me, that it feels really rich with possibility. And so that's more of a theoretical thing. I also my particular ideas about how this might all fit together into a version of inflation that resolve some of these other questions would involve having very interesting, but potentially complicated physics determining the universe on the largest scale. And so new data could really reveal something about that. And I'm excited. My grad student and his collaborators, Arslan Adel and collaborators, have recently done some work pursuing this subject called remote quadrupole measurements, which involve a trick of using different
other galaxies and their CMB observations. Is that the?
So it's sort of like observing a galaxy in a particular way that reveals how the CMB looks to that galaxy, and therefore pins down a much more precise picture of the larger scale features of the universe. So there's all kinds of things like that. I think polarization could reveal things. So I think there's a lot of interesting things that can happen with data. There's interesting things that can happen with theory, and I'm also really curious about there's things connected with the emergence of classical from quantum, which we hardly got to talk about, but the sort of how does the strangeness of quantum physics hide itself from our everyday life, that I feel are relevant to some of these topics as well. And I've been exploring all these different things actually. So I think there's lots of physics, science is, we like to say we take nothing on faith, and I think that's kind of true. We're at the end, we know, we've talked a little bit about the sociology of it, but at the end of the day, we can question anything. Maybe maybe wait for the next generation or whatever, but it happens. The one thing we take on faith is that science will continue to yield interesting results, and there's no guarantee. We embrace the adventure of seeing what happens by continuing to do science. And these are the kinds of areas, we try to imagine which areas are promising, and I think you and I have been discussing some really wonderful ones, and we got to jump in and check it out and see what happens.
Are you optimistic about us detecting polarization in the CMB that would truly show an influence of gravitational waves from the Big Bang, primordial gravitational waves?
Optimistic enough for people to support people doing it. And I would say I would say I don't feel I don't have a feeling like, oh, this particular model is so much better than that particular model, and it's going to yield a result, or it's not going to yield a result. I don't tend to live in that space. It's kind of like, what you've raised is something that would be answered in the space of these potentials that we were drawing on the screen a little while ago. Would it be this potential or that potential? I've actually found there's a lot of people, that's like a lot of bread and butter cosmology is done exploring that. It's not my greatest interest because, as I think I said, I find these bigger questions sort of looming in a way that will probably result in be about the breakdown of quantum field theory and other dramatic changes. And so I feel I don't feel attached. I don't spend my time figuring out which potential I like better than which other potential. And so but I think, I'm reminded of a part of my personal history from long ago, which is that I remember visiting Caltech, and I don't have a clear memory of who I was talking with, but I'm guessing it was Andy Lang. And this was very early in the days of inflation. And by the way, my personal experience with inflation was, we wrote this paper, Paul and I, and it instantly became this big hit. And a friend recently asked me, outside of science, asked me, so how did it feel? Like, how did you feel about that? And I said, I felt really wary because I wanted, and I was already aware of some of these bigger questions, and I wanted to make contributions that would be would be embraced as real science, not just 1 year, but into the future. And I could tell there was a lot of faddish thinking going on. I was very suspicious of the sort of the drama that was emerging with that, and I was shocked to find this observational cosmologist I encountered at Caltech, probably Andy Lang, saying, "Please, we need to know." This was before anyone had worked this stuff out. We need to know what you're predicting for the CMB so we can go out and measure it. And I was thinking, oh my God, these are the guys who hold the key to really understanding it, because these guys are going to take the data and tell us what's true. And I sort of felt like the world of theory at that time was a bit of a circus with wild ideas coming back and forth. And the idea that this very dignified, practical observer was looking to us for support seemed really surprising to me. Now I understand that the psychology, you don't want to go data unless there's something that's going to mean to someone. So I shifted, but it was part of my education to sort of journey through that. And I think I have enough interest that I want to work hard to help the people who are doing this measurement feel it's a good idea. I think it really is.
But let me ask you along those lines, though, what about the failure to find the B mode signature? Because obviously, as you've been saying, you can fiddle with the inflationary model to suppress the strength of the signal of the primordial gravitational waves. But would that then start to make you feel like you're tuning it again and moving away from a more convincing framework, or will it have no impact? If we don't find them, will it have any impact on your sensibility regarding inflation?
For my particular nature and the way I'm journeying through these questions, it will be very interesting, because it'll be a kind of boundary condition on what can work. But as I've been emphasizing, I feel that the much bigger questions are so likely to be disruptive if we can make any progress with them, that I don't get attached to this inflaton potential or that inflaton potential along the way. I more think of that as good. Now I can update. Now that gives me some constraint about how I can move forward. But that's my own personal. I think it's very important that science is done by many different people with many different sort of ways of defining their path. And so I'm glad other people are doing it differently, but this is my path.
Yeah. Well, look, it's a fascinating path, and this has been a great conversation. Unfortunately, I have to bring it to a close, but I'd love to have a part 2 at some point and investigate all the things that we touched on but didn't go into, like the quantum measurement problem and all that great stuff.
One of the ingredients to my favorite alternative, or sort of favorite way of trying to package inflation, involves equilibrium, and I know you've also worked on that, and I actually have a little bit of update from talking with Kumar Wafa recently. So there's endless things we should be talking about, and I look forward to
endless things to go. Yeah, so we'll definitely do a part 2, but until then, of course, best of luck making progress on these big questions, and maybe even by next time we'll shed new light on them, which would be wonderful. But it's been really exciting speaking to Andy, and I'm looking forward to the next time.
Thank you, Brian. I'm excited.
Thanks for joining us. All right, see you later.
Bye-bye.